introduce our speaker today. It is Nikolai Ivanovich Portenko. He is a corresponding member of our Academy of Science. And Nikolai Ivanovich is a world-famous specialist in the theory of diffusion processes. So it is a very big pleasure for all of us that he agreed to give us 2 lectures in this subject. Also, I must mention that maybe Shakir Kasimovich, Yakubjan, remember Nikolai Ivanovich because he visited Tashkent, he visited Uzbekistan. So maybe this is one of the reasons why Nikolai Ivanovich agreed to deliver lectures for us. And it is our pleasure to see him and hear his lectures. Nikolai Ivanovich, please.
Thank you. I'm going to show how to construct some diffusion processes whose drift is a very irregular function. It may be locally unbounded function or even a generalized function. But I will start from the simplest notions. Let us consider some system whose states form some space I denote it by X capital. So the point of this set is the state of my system. Our system will evaluate in time, so its position at the instant of time t will be denoted by x of t. So x time is non-negative, and x of t is a point from x. And this state changes as time goes on, okay? And we will consider stochastic system. It means that x of t is a random element from this space. So we have to endow this space by the structure of measurable space. Okay, so let us point out some family of subsets of X that are called measurable, and the family of all measurable space. The sets will be denoted by B, and B is a sigma algebra of subsets of X. Okay? Then we can speak about the event X of T is a point from gamma, if gamma is a measurable space, and T is an instant of time. This is a random event. Well, we can speak about the probability of this event. Okay, and how to describe the evolution of our system if it is a stochastic one? The best description will be as follows. Let us denote by F as the history. It is the history of our system. Георгий, там якісь звуки є. The history. It means that F S consists all the events that concern our system up to the instant of time S. Okay? So if I know, let us consider axis of time, let S is a present. So here is the past, here is the future. And if T is an instant in future, we can consider the probability that this event occurs, the conditional probability given history up to the present instant of time. This is the best description of a stochastic system. If we know these probability, we can predict its behavior in the future, at any instant of time in future, given all the information about behavior of our system in the past up to the present. Okay? But how these probability can be calculated? It is a very difficult problem. And at the very beginning of 20th century, Russian mathematician, a famous Russian mathematician, Markov, pointed out some systems that possess the following property. This probability conditional coincides with the probability that the same event occurs if only the location of our system in the phase space X X is called the phase space. Okay. Markov. Suppose that the system is such that this prediction coincides with this prediction. So all the information, this equality takes place almost surely, because this is a random variable, this is a random variable, and they coincide only almost surely. So the information about the behavior of our system before instant of time s is unnecessary to predict the behavior of our system in the future. Such a system, if some system possesses this property for any t, any s is less than t for any gamma from B, such a system is called Markov process. This is a stochastic process that is called Markovian. This property is called Markovian property. Okay, and now let us observe that the probability that is written on the right-hand side of this equality is a function of x of s. If x is a nice space, for example, x is a d-dimensional Euclidean space, okay, then there exists such a function. I would like denote it by p, but this is not that p, because this is the probability measure on the space of elementary events, and this is a function of what? It depends of s, x, t, gamma. And this function is such that if I substitute here x of x instead of x, I obtain this probability. Okay, and as far as I consider Markov system, so it coincides with this, the best prediction for our system in the future. Okay, and and I would like to look at this function. It must be, you see, we have substitute instead of x a random variable. So this function must be measurable in x. P S x t gamma as a function of x must be measurable. Be measurable. For fixed S, T, and gamma. The second, this function, the function of gamma, must be probability measure. Probability measure. Okay, and the third property, if you have 3 instants of time, S, tau, and t, then P, S, X, T, gamma is equal to the integral or X, P, tau, Y, T, gamma, P, S, X, T, dy, tau dy. This relation is a consequence of Markov property. You see how in what way we can undergo into set gamma at the instant of time of t if we have some instant of time tau between s and t. So from x at the instant of time s, our system must undergo at some point of x at the instant of time of tau, and then after that it must undergo from that y to subset gamma. If our process is not Markovian, then I should write here. I have to write here not only tau y, but also sx. Our system at the instant of time s was at x. At the instant of time tau was at y. And then this is the probability that in this instant it is in gamma. But because our process is Markovian, this information is unnecessary to calculate this probability. So we have this equation, and this equation is called Kolmogorov-Chapman equation. You see, it can be written, this equation can be written under the condition 1 and 2. We should integrate this function, and we may integrate only measurable function, and we should integrate with respect to this measure. This measure, it is our second condition. This must be measured with respect to this argument. So this is the Kolmogorov-Chapman equation, and its solution generates some Markov problems. because we can calculate all joint distribution for random elements xt1, xt2, so on, x, and knowing, if we know this function, it is called transition probability. This function is called transition probability. If you know transition probability and distribution at the instant of the initial time, t0, if I know distribution of my system at the initial instant of time, I can write down the joint distribution of any such family of random elements in X. So it can be written the probability that this collection of random elements can be calculated the following way. Integral over x mu x integral over gamma 1 p t1 p0 t0 p t0 x 1 y1 integral over gamma 2 p t1 y1 t2 y2 and so on, and the last one integral over gamma n p n minus 1 y n minus 1 t1 tn dy n. Is an easy exercise. So we know all the finite dimensional distribution of our system, our Markov process. If you know initial distribution and transition probability. In 1931, another famous Russian mathematician, Kolmogorov, pointed out a class of stochastic processes that later came to be known as diffusion processes. He proposed how to linearize equation, the equation of Kolmogorov-Chapman, the equation of the Kolmogorov-Chapman equation is not linear. That equation contains all the Markov processes. Yes, if our phase space is not very complicated. So every solution to the Kolmogorov space equation gives us some example of Markov process. It would be very good to describe all the solutions of Kolmogorov-Chapman equation, but this problem looks like a very, very difficult. And Kolmogorov in 1931, as I mentioned, proposed some method how to linearize that equation, Kolmogorov-Chapman equation. He supposed that transition probability that he supposed that Markov process is such that its transition probability has the following properties. This is the following properties. The first one. I would like to suppose that X is d-dimensional Euclidean space and B is the smallest sigma algebra of subsets over D that contains all the open subsets of RD. Okay, this sigma algebra is called sigma algebra of Borel measure sets. We will now consider systems in such a process, and if I have some Markov process, I have its transition probability in this case, and suppose that this transition probability has the following properties. The first one, integral over b epsilon of x by denoted by b of x, the closed ball in RD. That is the set of all y such that norm y minus x is less than or equal to r. R is positive and x is a point from RD. And I will use the following notation. If gamma is a subset of RD, then gamma C is the complement RD minus gamma. So the integral over the complement to ball b epsilon of x x of PSXT divided. Right? It is the same. It can be written simpler. PSXT B epsilon of x C. Okay. The first Komodorov's supposition was the following one. If I divide this probability by t minus s, then this goes to 0 as t goes to s for fixed, for any fixed epsilon, and for all x so you see, what does it mean? If our process starts from some x, then the probability that it occurs at some points outside of this ball, this probability is very small. You see, it must, this probability, it must be as small that when we divide it by t minus s, it goes to 0. So it's very strong. This means, in some sense, I will discuss this question some more later. Okay, the second one. If I calculate integral over ball of displacement y minus x ps x t divided. The condition is this must go to some limit. Limit exists as t goes to s for some epsilon, and for all x and s, where s x and s. What does it mean? This is the mean value of displacement within this interval of time st. And if t is close to s, and we divide this mean value on t minus s, well, this limit exists. And this third, if we divide following: y minus x theta. This is the projection of displacement, of our displacement on the direction theta square x t y. This limit also exists as t goes to s for some epsilon and all x from RD and s. So this is some supposition about continuity of the process. You see, this undergoing is very probability that such a change occurs is very small if we consider small interval of time. And there exists some limit like velocity of our system, mean velocity, okay? And this is the position that means that our system has not only macroscopic movement, but also microscopic, because if you consider some dynamical system, then it displaces, if the velocity exists, then square of displacement has this must go to 0, because divided by t minus s squared, the limit exists. And now I forgot to say that here theta is an arbitrary point in RD. This must exist for any arbitrary theta. Okay? Now, it is a very simple exercise to prove that if the first supposition is fulfilled, then limits in property 2 and 3 exist for any epsilon, and these limits do not depend on epsilon. So this limit is some vector valued function a s x. Okay, and this limit is a quadratic form. Bsx and this operator Bsx must be positive definite, because this expression is non-negative. So if the process is diffusion in this sense, then we have two functions, vector valued and operator valued function, A of Sx and B of x. A of Sx means that our system or our particle, if our system is a particle, for example, a very small particle in a liquid, okay, so there can be some macroscopic motion, for example, stream in the liquid, okay, and this function gives us the local velocity of our medium at the instant of time s, at the point x of our medium. And this function characterizes microscopic motion. Our particle takes part in microscopic motion, and dsx it characterizes that macroscopic motion. Why I write here integrals over ball of finite radius, because we do not know our transition probability must may the integral over all space may not exist. But if the moment exists, then we can verify it maybe somewhat simpler. Condition. The first one, if there exists some delta positive, that this integral goes to 0 as t goes to s to prime. If the integral y minus x over all space r d t s x t dy some function a s of x for all s and x. The third one, about the third Kolmogorov condition, y minus x squared P dy goes to d s x as goes to x. If we can, if psx t dy has moments of this, of the order a little bit more greater than 2, then we can verify if we can verify that these properties are fulfilled, then our process is diffusion in the sense of Tomodor. And I propose you to the following exercise. Let P gamma be given by the following integral: 2p t minus s to the power minus d over 2 integral x minus y minus x to the power square over 2 minus x. Okay. The exercise consists in verifying that this function satisfies the Kolmogorov-Chapman equation, and it is diffusion in this sense. It satisfies these 3 properties, and AS is 0 identically, and BS is identity operator for all S and X. So we arrive at the following conclusion. This is a transition probability, and it is a transition probability of a diffusion process, and this function A of Sx is called drift, and this operator is called diffusion operator. If you fix some basis in our space and consider the matrix of this operator in that basis, so this is diffusion matrix, diffusion vector, drift vector. So this process is a diffusion, and for it, drift is 0 identically, and the diffusion operator is identity operator. Okay. Now I would like to to formulate some result that allow one to consider Markov processes with continuous paths, with continuous trajectories. That condition is, it can be formulated in metric spaces, but I would like to formulate it for RG. So consider transition probability density as x t d epsilon of x c. This probability was in the first condition of the definition of Kolmogorov's definition. Okay, let us consider. We know that it must, in Kolmogorov, it must be all small of t minus s. All small of t minus s for fixed epsilon and for fixed x and s. Now we would like to pose somewhat more of this function. Let us consider supremum over all x from Rd of this probability. And let us consider one more supremum over all s s plus h t is a fixed number, okay? H is some positive number, and epsilon is positive number. Then this supremum is a function of a function alpha of epsilon of t and h. And the condition is, sounds like this. If this is a theorem, if alpha epsilon t of h divided by h goes to 0 as h goes to 0 for fixed epsilon and t, then there exists modification of our process such that its trajectories are continuous. This theorem, if then there exists continuous Markov process with this transition probability density. The theorem was proved by Dinkin, professor of Moscow University, Dinkin, in 1952. Okay, this is, now let us continue this exercise. prove that this transition probability density satisfies this condition of this Dayton's theorem. So there exists a continuous Markov process with this transition probability, This function that is integrating here is called transition probability density. It is clear that transition probability is determined by this density. So we can say that there exists a continuous Markov process with this transition probability density. This continuous Markov process is called Brownian motion, or in solid literature is called Wiener process. A continuous Markov process with this transition probability is called Wiener process or Brownian motion. Brownian motion. Okay. And now I have 5 minutes. Yeah?
Yes, yes.
Oh. Now, I would like to formulate on Kolmonov's theorem it was proved in 1931 in his very big paper that was published in German. And somewhat later it was translated into Russian, and it can be formulated as follows. Theorem. If x t divided, I consider the Euclidean space as our phase space. If is transition probability of a diffusion process, diffusion, and a given function phi of y such that the function viewed as x t phi given by the integral phi of y phi s x t y. If this function and if given function is such that this function is twice continuously differentiable with respect to this argument, with respect to x. Twice continuously differentiable in X, then it is differentiable with respect to S and satisfies the following, this function satisfies the following equations: du ds plus a s x. This is the drift gradient of u plus 1/2 trace b s x d 2 u equals 0, where you see the second derivatives with respect to x of this function forms a matrix. Okay, and bsx in our basis is also matrix. This is product of two matrices, and then we take trace. Okay, and here is gradient. This is a vector. Gradient is of this function as a function of x. All my time is over, and initial condition sounds like this: USXT goes to phi x as S goes to T for all x from R. You see, Kolmogorov supposed that our process is diffusion, and if this function is smooth enough in this argument, then it is differentiable in X, and it satisfies this equation and this initial, because it is not initial, but finish instant of time. Okay, and this equation is linear. So he linearized the Kolmogorov-Chapman equation in this way. I will speak about, I will start my next lesson with this statement. And today my time is over. Thank you very much.
Okay, thank you for the attention, and thank you, Nikolai Ivanovich, for your interesting introduction to diffusion processes. Maybe somebody have questions, please.
Так, Косевич хотел что-то сказать.
Да-да, пожалуйста, Якубжан Хусанбаев.
Шакир Касимович хотел что-то сказать. Андрей.
Шакир Касымович, слушаем вас, Шакир Касымович.
Шакир, у вас микрофон отключен? Шакир, какая-то проблема у вас там?
слухачами були.
Полторака, ничего не слышно.
Я думаю, що я збив у них охоту займатися математикою. I'm ready to answer questions.
Okay.
Николай Иванович, очень интересно, это, конечно, видение. Сейчас он звонит куда-то. Хасимович хотел сказать это. Да, Шакраке.
Buyurun, aloqa
Вот сейчас слышно вас, хорошо слышно.
это самое.
Ну, через телефон можно зайти.
А?
Да, говорите, мы вас слушаем.
Да, ну хорошо. Да, мы только что послушали очень интересный доклад Николая Ивановича Порtenко. Мы с ним давно знакомы, я не знаю, сколько лет, Коля, мы с тобой знакомы. Вот. Ну, я обновлю свой самый украинский, обновлю в смысле сведения о дружбе наших узбекских и украинских математиков. Потому что я вообще ровесник Галины Ситая. Да. Вот. Во многих и Николай Иванович и Ситая были учениками, значит, когда я начал наукой заниматься, вот и мы вместе начали заниматься наукой, но Николай Иванович, по-видимому, чуть попозже. Вот. Я Николай Иванович, я приветствую вас на нашем семинаре и желаю вам успехов. А что я хочу сказать, что Николай, я даже начал говорить, что Николаем Ивановичем, значит, мы были во многих конференциях. Я его знаю примерно с того времени, когда первый раз в Ужгороде, в Западной Украине, была организована первая школа коллоквиум для молодых специалистов.
В 1964 году.
В 1964 году, да, в 1964 году.
Да.
А вот я теперь я понимаю. Ну, я тогда тебе говорил на ты, в общем, Николай, ты,
Ну, я тоже могу на ты.
Будь здоров и благополучен, как говорится. Спасибо за доклад.
Спасибо. Я был на советско-японском симпозиуме в 1975 году в Ташкенте. А в 1972 году был в Фергане, там была...
Да, я помню.
Так что я бывал в
вашем... Я не помню, ты у нас в этот конгрессе Бернули был или не помню? Тогда я не помню, что твой участок. В 1986 году.
Но в 1986 я не был.
Да. Я сразу подумал,
Это Бернулиевский.
В конгрессе. Да. Ну, будь здоров, Николай.
Спасибо, ты тоже будь здоров.
Okay, maybe for today we will finish our session, and we will meet one another next week with the continuation of the lecture of Nikolai Ivanovich. Thanks, everybody. Bye.
Thank you.
Bye.